The purpose of this lab was to observe the motion of a falling object which is both affected by weight force and drag force. Newton's second law, or the momentum principle, were major players in this lab. In this lab, a paper bag was dropped and its motion was analyzed using Tracker and modeled using Python. The computational model, with and without drag, and the experimental models were then modeled and were then plotted and compared to understand the net force acting upon the system, which includes gravity and drag force, and the object had then reached its terminal velocity. The computational model with drag force proved to be the better representation of the experimental model. The object will accelerate at a rate which is inversely proportional to its mass, and the object moves in the negative y direction because it is being dropped from a height of 1.414 meters. Here is the video of the bag being dropped and the corresponding graph using point mass. The parameters in the experimental model were time and y position, giving velocity by the slope of the graph. Measurements were calibrated to be the distance of the drop and set to be 1.414 meters. The axis was tilted to be negative 90.1 degrees because of the way the bag was initially held. The plotted graph from the experimental model first shows a small plateau, then sharply dips down until terminal velocity is reached, which is noted by the linear constant slope towards the end of the drop. Newton's second law played a major role in this lab. Here, net force is not equal to zero because there is not a constant velocity and therefore an induced acceleration. The forces that make the net force not equal to zero are the weight and drag force. This last equation is inputted directly into the code. The code was first initialized using the paper.m variable, setting the mass of the paper bag to be 0.023 kilograms. Since the bag started from rest and at the initial position 000, the paperbag.pos and paperbag.vel variables are both set to be the vector 000, and the time of the drop begins at t equals 0 seconds. The time step of the computational model is set to be 0.003 seconds in order to produce accurate results. Additionally, the proportionality constant g is set to be 9.8 meters per second squared, which is the magnitude of the gravitational force on the surface of the Earth. The proportionality constant b, which is the magnitude of the drag force, was experimentally determined through trial and error to be 0.02868 newton-seconds per meter. Now, onto the motion prediction loop. As per Tracker, the while loop is set to be from 0 to 0.702 seconds. The weight force of a system is said to be F equals ma as per Newton's second law. Therefore, the weight force is inputted to be the mass of the paper bag times the j hat vector times negative 9.8 meters per second squared because the bag is moving in the negative y direction. F net therefore simply consists of the weight force, and this line is a direct input of Newton's second law. The paperbag.pos is similarly updated and time is advanced by the time step. When the code is run, the only force on the paper bag is the weight force, which is shown by the downward yellow arrow, and the computational model is very different from what actually occurred in the experiment. This is because a very important vector force is missing, the drag force. This can be set into the code for a more accurate portrayal of the experiment by setting F drag to be negative b times the magnitude of the velocity of the bag squared and adding F drag to the overall net force. When the code is run, a much more accurate visual of the experiment is shown by the two vectors. One pointing upwards, the blue arrow is the drag force, and one pointing downwards, the yellow arrow is the weight force. Here, the computational model without drag and with drag. The experimental model were plotted. The computational model without drag force overpredicted how much the bag actually moved. This is because the weight force was not the only force acting upon the bag. Now, when comparing the computational model with weight and drag force and the experimental model, the plotted points were very, very close to each other at both the beginning and the end. The terminal velocity is reached around 0.6 seconds into the video. This can be proven by the constant slope and therefore no acceleration. The terminal velocity of a falling object is defined by when the sum of the drag force is equal to the downward force of gravity acting on the object, and since the net force is then zero, the object will have a constant or terminal velocity. Some final thoughts of the lab are examining the velocity versus time model. The computational model with drag is much more accurate in predicting terminal velocity. This is because the graph starts to level out, meaning there is a constant velocity, whereas the graph without drag force continues to slope downward sharply. When looking at velocity versus time graphs, this becomes even more evident because the velocity continues on without drag force, whereas the velocity begins to slow down and reach terminal velocity. Secondly, if the object was initially thrown downward, the paperbag.vel variable is changed. In this case, the terminal velocity would be the same, but since the object is thrown downwards, the drag force would surpass the weight force and the object would first decelerate.